Welcome back to the deep dive. Today, we are going inside, really inside, the structure that literally holds us all up. We
Mm.
are exploring the foundational architecture of the human body, the master structure that's, well, it's simultaneously a bank, a factory, a protective shield.
And the ultimate scaffolding. You
Yeah,
got it.
exactly.
That's right. Our focus today is the engine room, you could say, the core support structure, the axial skeleton.
The axial skeleton.
Yeah, we're talking about the 80 bones, the skull, the spine, and the rib cage that form that central axis. This framework, it dictates our posture, protects our most vital organs, and crucially, bears our entire body weight.
Wow. And the stack of anatomical sources you shared with us is, well, it's incredibly detailed. So our mission today is to take you, the listener, beyond just listing these bones.
Right, we want to get into the dynamic, the living nature of bone tissue itself, how it builds itself, how it maintains itself.
And the architectural genius, really, of this central framework, the skull, spine, rib cage.
The goal is definitely to move past that static image, the skeleton hanging in a classroom.
Right, the Halloween decoration.
Exactly. We need to internalize that this is a perpetually active, highly specialized system. And we'll be using analogies throughout this dive.
Good. Analogies help.
Yeah. Hopefully to make this complex biological framework feel a bit more intuitive, help it stick in your memory.
Okay, let's unpack this immediately then. When most people think of bone, they think of something dry, brittle, maybe dead. But we have to start by establishing a crucial point. Bone is not inert material. It's a complex organ. Why is that distinction so important?
It's absolutely vital. Because an organ, by definition, it has to consist of multiple integrated tissues working together for a common function.
No.
Osseous tissue, which is the hard, mineralized part we usually think of, that's just one component. Bone also contains dense connective tissue, cartilage, epithelial tissue, nervous tissue.
Nerves, too.
Oh, yeah. And, crucially, blood vessels and adipose tissue, fat.
So it's really a whole ecosystem packed in there.
Exactly. And unlike, say, a piece of rock, bone is incredibly dynamic. It is continuously growing, remodeling itself, repairing itself. Constantly, through complex cellular processes that respond to things like gravity, mechanical stress, even hormonal signals. It is quite literally alive.
That level of complexity, that dynamism, well, it must mean it has multiple jobs to do, right?
For sure. Our sources highlight 6 core functions. The why the skeleton isn't just a coat rack.
Okay, let's hit the big ones.
All right. The first 2 are probably the most familiar. Support, it acts as the rigid internal framework. Think of it like the steel scaffolding of a building.
Got it. Holds everything up.
Right. It supports all the soft tissues and provides the attachment points for muscles, which lets us interact with the world.
Makes sense.
Second, protection. This is our internal armor plating, you could say.
Like a night suit.
Pretty much. The skull is a dedicated helmet protecting the brain. The bony thorax, the rib cage, shields the heart, lungs, major blood vessels.
And the spine.
The vertebral column is the ultimate conduit protector for the delicate spinal cord running right through it.
Okay, support and protection. What's third?
Third, they assist in movements. Bones act as rigid levers.
Levers? How so?
Well, muscle contraction provides the force, the pull, but the bone provides the fixed point, the fulcrum, that's needed to translate that pulling force into actual motion.
Ah, like lifting your arm or taking a step. The muscle pulls, the bone moves.
Precisely. Without the rigid lever, the muscle contraction wouldn't achieve much useful movement.
Okay, now we get into the functions that are maybe less obvious, but you suggested maybe even more critical.
Yeah, I think so. The fourth is mineral homeostasis. This is huge.
Homeostasis.
Maintaining balance, right?
Exactly. Bone is the body's central mineral vault or bank. It holds something like 99% of the body's stored calcium, plus substantial amounts of phosphorus.
Wow, 99% of the calcium, so it's like a bank.
It's exactly like a bank. And this role is relentless, operating minute by minute when your blood calcium levels dip too low.
Which is bad for nerves and muscles. Very bad. So parathyroid hormone, PTH, signals the bone. Release some calcium into the bloodstream. We need it now.
So the bone sacrifices a bit of its structure for immediate needs?
It does. Conversely, if blood calcium gets too high, another hormone, calcitonin, steps in and signals the bone to absorb and store the excess. Deposit it back in the vault.
So it's this constant deposit and withdrawal system.
Absolutely. And interestingly, the health of your nervous system and muscle function often takes priority over, let's say, the momentary structural integrity of your bone. The body makes choices.
Fascinating. Okay, function number 5.
Hematopoiesis. Fancy word for blood cell formation.
Ah, the blood cell factory. You mentioned that analogy.
Exactly. Red blood cells, white blood cells, platelets, they're all produced within the red marrow found inside certain bones.
Is red marrow in all bones?
Ah, good question. Critically, in infants and young children, pretty much all bone marrow is red and actively producing blood cells. They're growing fast and need lots of blood.
But that changes.
It does. As we age, much of that red marrow converts to yellow marrow, which is primarily found in the central shafts of the long bones. And that yellow marrow handles the sixth function, which is triglyceride storage, fat storage.
So bones store fat, too.
They do. The yellow marrow is mostly adipose tissue. It stores fat as triglycerides, serving as a long-term chemical energy reserve for the body.
Like a pantry for energy.
A pantry, exactly. But here's the really incredible part. The body actually retains the ability, under conditions of severe physiological stress, like major blood loss.
Quick trauma.
Yeah, exactly. It can trigger a conversion process, turning that yellow fat-storing marrow back into red blood-producing marrow.
Wow. So the factory can reopen closed production lines if there's an emergency.
That's a perfect way to put it. The secondary production lines can fire back up. It shows amazing biological resource management.
That really is fascinating. So we have this multifunctional organ, a bank, a factory, armor, scaffolding, levers. Let's look at the actual blueprints now. What does the macroscopic structure, the big picture of a typical long bone, say the humerus in the upper arm, tell us about its design?
Okay, the long bone is kind of the architectural prototype. Good example to start with. The main elongated central part is the diaphysis. That's the shaft. Think of it as the main weight-bearing column.
The shaft, okay.
Then at the proximal and distal ends, the top and bottom, you have the bulbous, often slightly wider, epiphysis. Plural is epiphysis.
And those are the ends that form joints.
Exactly. They're specialized for articulation, for meeting other bones. They usually have a covering of smooth cartilage.
And connecting the shaft to these end caps.
The region is the metaphysis. It's where the diaphysis flares out to meet the epiphysis.
Yeah.
In growing bone, this is where the growth plate is located.
Ah, okay. Now you mentioned tissues covering it. What's on the outside?
Structurally, every surface is covered. Externally, the periosteum is absolutely critical. It's a tough, double-layered membrane made of dense, irregular connective tissue.
Like a strong shrink wrap.
Yeah, or a really tough casing around the whole bone. It's incredibly rich in blood vessels and nerves. Very sensitive. Oh, yeah. If you've ever had shin splints or taken a hard knock on the bone, that acute sharp pain, that's largely the nerves in the periosteum screaming at you.
Ouch. Okay, so that casing isn't just passive wrapping, it's active.
Very active.
Yeah.
It provides attachment points for tendons and ligaments, and it contains bone-forming cells crucial for growth and width and for fracture repair.
Got it. Now, inside that main column, the diaphysis.
Inside, there's the medullary cavity. It's the central cylindrical space running pretty much the length of the diaphysis. In adults, this is typically filled with that yellow marrow we talked about.
The fat storage.
Right. And just as the periosteum lines the outside, there's a thin membrane lining the inside surface of the walls of the medullary cavity, the trabeculae of spongy bone. That's the endosteum.
Like a liner inside the pipe.
Perfect analogy, the pipeline liner. And it's also crucial because it houses the critical cells responsible for bone remodeling, building up and breaking down bone from the internal side.
Okay, macrostructure clear. Now let's drill down. You said bone is dynamic, it needs a crew. Who are the actual workers on this constant construction and demolition site at the microscopic level?
Right, we have 4 highly specialized cell types doing the work. The cycle really begins with osteoprogenitors.
Progenitors, like predecessors.
Exactly. These are the stem cells derived from mesenchyme. Think of them as the raw labor pool, undifferentiated, just waiting for the signal to specialize into bone builders.
Okay, so who are the builders?
That's the primary construction crew, the osteoblasts. B for building.
Osteoblasts build, got it.
Yes, they're the bone-building cells. Their job is to synthesize and secrete the organic components of the bone matrix, mostly collagen fibers, and initiate calcification. This unmineralized matrix is called osteoid.
So they lay down the framework first.
Precisely. And once an osteoblast has done its job, secreted matrix all around itself, and becomes completely encased within that matrix, it matures. It differentiates into the third cell type.
Which is?
The osteocytes.
Osteocytes. What do they do once they're walled in?
The osteocytes are fascinating. They become the maintenance staff, you could say, the facility managers embedded within the structure.
Maintaining it?
Yeah. They maintain the daily metabolism of the bone tissue, exchanging nutrients and waste with the blood. They also act as stress or strain sensors. They can sense mechanical loading on the bone.
And communicate that?
Exactly. They communicate with each other and with the surface cells through tiny microscopic channels called canaliculi. They essentially signal if bone needs to be reinforced or perhaps resorbed. They keep the tissue healthy.
Okay, builders and maintainers. But you mentioned demolition.
You can't have an eternal construction project without a demolition team. That's the osteoclasts. C for chew or consume.
Osteoclasts. Bone eaters.
Bone resorbers is the technical term, but eaters works. These are huge, multinucleated cells derived from the same stem cells that produce white blood cells. Their job is resorption.
Breaking down bone.
Yes. They settle on a bone surface and secrete powerful lysosomal enzymes and acids that digest the organic matrix and dissolve the mineral crystals.
Why break down perfectly good bone?
Several reasons. To release stored minerals like calcium into the blood when needed, as we discussed. Also to remove old, micro-damaged, or simply unnecessary bone matrix as part of the remodeling process. It clears the way for new construction.
Ah, so that balance osteoblasts building, osteoclast demolishing, that's the secret to the bone's adaptability and maintenance.
That's the heart of bone remodeling, yes. A constant coordinated dance.
Now, microscopically, you mentioned the bone material itself comes in two main flavors, structurally speaking.
That's right. Based on porosity, we have highly dense compact bone and much more porous spongy bone.
Okay, let's start with compact bone. Dense and strong.
Yes, compact bone is the strongest type. It makes up the dense outer layer of all bones and the bulk of the diaphysis of long bones. It provides protection and support and resists the stresses produced by weight and movement. It has very few spaces visible to the naked eye.
And its structure, you said, is like engineered piping.
It is. It's organized into repeating structural units called osteons, or Haversian systems. These are fundamental. If you think of the diaphysis as a thick-walled pipe, then the osteons are like thousands of tiny, concentric, tightly packed smaller pipes running parallel to the long axis of the bone. This orientation is key for resisting stress along the length.
Concentric pipes, like growth rings on a tree.
Very similar visually. Each osteon consists of concentric rings of calcified bone matrix called lamellae. Think of it like rolling up a sheet of paper tighter and tighter.
Okay.
That layered structure provides incredible resistance against bending or twisting forces. And right at the very center of each osteon, running down its core, is the central canal, or Haversian canal.
And what's in that central canal?
That's the utility conduit.
Yeah.
It houses the small blood vessels and nerve fibers that serve the osteon cells.
But how does the blood supply get from the outside surface, the periosteum, deep into these central canals within the dense, compact bone?
Ah, great question. Through transverse channels called Volkmann's canals or perforating canals.
Perforating? They punch through.
Exactly. They run perpendicular or transverse to the long axis into the central canals. Think of them as cross streets connecting the main avenues, central canals.
Okay.
These perforating canals connect the blood vessels and nerves from the periosteum on the outside and the endosteum and medullary cavity on the inside with the network of central canals. It ensures the entire dense structure is vascularized and innervated.
A really intricate plumbing and wiring system within the steel pipes.
Precisely. Now, in stark contrast to that highly organized, dense structure, we have the internal architecture.
Which is spongy bone, also called trabecular bone.
Right? Spongy or trabecular bone. It's much lighter and more porous. You typically find it in the epiphyses of long bones, lining the medullary cavity and making up the bulk of short, flat, and irregular bones.
And structurally, it's different? No osteons?
Correct. It completely lacks the organized osteons of compact bone. Instead, its lamellae are arranged in an irregular branching network of thin columns called trabeculae.
Trabeculae, like little beams or struts.
Exactly. These trabeculae branch and interconnect, forming a lattice-like structure. The spaces between these struts are filled with red or yellow bone marrow.
The structure, you said, is like an internal honeycomb scaffolding. What's the functional brilliance there? Why not just solid bone?
Several key advantages. First, efficiency and weight. Spongy bone greatly reduces the overall weight of the skeleton. Imagine if your bones were solid, compact bone, we'd be incredibly heavy.
Right. Makes sense.
Second, strength where needed. The trabeculae aren't random. They are oriented precisely along lines of mechanical stress. Like the internal struts and braces in a bridge or a building, they provide maximum strength with minimum material.
Adapting to the forces placed on that specific bone area.
Exactly. And third, and critically important, those numerous open spaces within the honeycomb structure provide the ideal protected environment for housing the red bone marrow.
The blood cell factory needs its space.
It does. Spongy bone is the primary site of hematopoiesis in adults. So the structure perfectly integrates lightness, stress resistance, and the housing for blood cell production.
That really connects structure and function beautifully. Okay, let's shift gears slightly. We understand the material, its cells, its types. How are the 206-ish bones in the adult skeleton categorized? You mentioned shape is a key classifier.
It is. Classifying bones by their overall shape gives us immediate clues about their primary function within the skeleton. There are 4 main categories, though some add a 5th, sesamoid.
Let's stick to the main 4 for now. First up.
Long bones. Pretty self-explanatory. They are considerably longer than they are wide. They consist of a shaft, diaphysis, and 2 distinct ends, epicesi. Think of the major limb bones: the femur, thigh bone, humerus, upper arm, radius, ulna, tibia, fibula. Even the metacarpals in your hand and metatarsals in your foot count as long bones, despite their smaller size, their primary role.
Acting as levers for movement.
Exactly. They are the body's primary levers, allowing for broad ranges of motion when muscles contract.
Okay, second category.
Short bones. These are roughly cube-shaped, nearly equal in length and width.
Where do we find those?
Primarily in the wrist, the carpals, and the ankle, tarsals. Their main job isn't broad movement, but rather providing stability and acting as really effective shock absorbers in these complex joint areas.
Like sturdy little blocks absorbing impact.
Precisely. Third category, flat bones.
Flat, like plates.
Generally thin, often flattened, and usually a bit curved. Think of the bones of the skull protecting the brain, the sternum, breastbone, the ribs, and the scapulae, shoulder blades.
And their function follows the shape.
Absolutely. Their primary role is extensive protection for underlying organs, or providing broad surfaces for muscle attachment. Protective shielding is a good analogy.
Makes sense. And the last main category?
Irregular bones. These are the ones with complex shapes that just don't fit neatly into the other categories.
The oddballs.
The highly specialized components. Examples include the vertebrae of the spine, certain facial bones, like the sphenoid or ethmoid deep in the skull, and the hip bones.
So their unique shape is tied to a very specific job.
Exactly. Their varied shapes often result from accommodating multiple functions: protection, support, muscle attachment points, forming joints. They're like highly specialized interlocking machine parts.
Okay, that classification helps visualize the diversity. Now let's talk genesis. Bone formation, or the technical term ossification. How is bone tissue actually created from scratch during development?
Right, ossification. Our sources break down the 2 fundamental developmental pathways by which bone forms.
2 ways to build bone.
2 main ways it starts forming during embryonic and fetal development. The first, and perhaps simpler way, is intramembranous ossification.
Intramembranous, within a membrane.
Exactly. In this process, bone develops directly from or within sheets of mesenchymal connective tissue, basically. Embryonic connective tissue. There's no cartilage stage first.
How does that work? Mesenchymal cells just become bone builders.
Pretty much. Mesenchymal stem cells cluster together, differentiate directly into osteoblasts, start secreting the osteoid matrix, and it gets calcified. It's a more direct route.
Like laying bricks directly onto some kind of foundation membrane.
That's a perfect analogy. Laying bricks directly on the membrane. This process is how most of the flat bones of the skull, many facial bones, and importantly the clavicle, collarbone are formed. It's efficient for creating wide protective shields relatively quickly.
Okay, direct bricklaying. What's the second method?
The second, and the pathway that forms most of the skeleton, especially the long bones in the base of the skull, is endochondral ossification.
Endochondral, inside cartilage.
Precisely. This is a much more complex, multi-step process where bone tissue replaces an existing hyaline cartilage model.
Replaces cartilage, so you build a cartilage version first.
Yes. First, a miniature hyaline cartilage model of the future bone develops from mesenchymal cells. Then, starting usually near the center of the future shaft, this cartilage begins to break down and is systematically invaded by blood vessels and bone cells, osteoblasts and osteoclasts, which then deposit bone matrix, replacing the cartilage.
So the analogy here isn't laying bricks directly.
No. The analogy our sources suggest is building a structure using a temporary detailed wooden frame. That's the cartilage model. And then over the course of development, you methodically dismantle that temporary wooden frame piece by piece and replace every single piece with permanent high-strength steel that's the bone.
Wow. That sounds much more involved. Why the 2-step process?
Cartilage can grow rapidly by division of its own cells, interstitial growth, allowing the model to lengthen quickly during fetal development. Bone matrix is too rigid for that kind of internal expansion, so the cartilage model provides a template that can grow quickly, which bone then replaces more methodically.
Okay, that makes sense. And that replacement process, that endochondral ossification, it doesn't just stop at birth, right? It continues.
Absolutely. It governs our postnatal growth and length. Long bones continue to lengthen throughout childhood and adolescence entirely due to ongoing activity at the epiphyseal plates, often called the growth plates.
Ah, the growth plates. I've heard of those. They're cartilage.
Yes, they are residual plates of hyaline cartilage located in the metaphysis, sandwiched between the epiphysis and the diaphysis.
So how do they make the bone longer?
It's a beautifully coordinated process with 4 functional zones within the plate. On the side closer to the epiphysis, chondrocytes, cartilage cells, are rapidly dividing and multiplying, thick of them stacking up like coins. This pushes the epiphysis further away from the diaphysis, effectively lengthening the bone.
So the cartilage itself expands.
It expands.
Yep.
Then, on the side closer to the diaphysis, the older cartilage cells enlarge, die off, and the surrounding cartilage matrix calcifies. Then, osteoclasts come in to remove the calcified cartilage, and osteoblasts follow right behind, depositing actual bone matrix onto the remnants.
So cartilage grows on one side, gets replaced by bone on the other side.
Exactly. And crucially, as long as the rate of cartilage growth on the epiphyseal side keeps pace with the rate of cartilage replacement by bone on the diaphyseal side, the epiphyseal plate maintains a constant thickness, but the bone itself gets longer.
That's clever. It's like a conveyor belt adding length.
It really is. And this is why an X-ray of a child's hand or leg shows those distinct dark gaps where the growth plates are, because cartilage doesn't show up as brightly as dense bone.
Okay, so what stops this process? Why don't we just keep growing taller?
Hormones. As adolescence winds down, typically between ages 18 and 25, depending on the bone and the person, hormonal changes cause the rate of chondrocyte division to slow dramatically.
The cartilage growth slows down.
Right. But the osteoblasts keep working, replacing the remaining cartilage with bone faster than it's being produced. Eventually, the epiphyseal plate thins out completely, the cartilage disappears entirely, and the bone of the epiphysis fuses solidly with the bone of the diaphysis.
That's called epiphyseal plate closure.
Exactly. Once that fusion occurs, signaled by the appearance of the epiphyseal line on an X-ray, longitudinal growth and length stops, the temporary frame replacement is complete.
And you mentioned hormones drive this whole timing. This process seems orchestrated.
Oh, absolutely. It's under intricate hormonal regulation. It's actually quite surprising how such a massive, seemingly rigid structure like the skeleton is so finely controlled by tiny chemical signals from distant glands.
Like which ones?
The major conductor during childhood is growth hormone, GH, secreted by the pituitary gland. GH directly stimulates the chondrocytes in the epiphyseal plates to divide and multiply.
So GH says grow faster.
Essentially, yes. But growth needs to be proportional, balanced. That's where thyroid hormones come in. They're essential modulators, ensuring the skeleton develops in the correct proportions. A deficiency in thyroid hormone during childhood can lead to stunted growth and disproportionate limbs.
So GH provides the gas, thyroid provides the steering.
That's a decent analogy, yeah. And then during puberty, the sex hormones estrogen in females, testosterone in males, cause that dramatic growth spurt.
They accelerate things.
They significantly accelerate chondrocyte division and osteoblast activity, leading to rapid lengthening. However, paradoxically, these same sex hormones are also the primary signalers for the end of growth.
How so? They speed it up, then stop it.
Exactly. They promote faster growth initially, but they also eventually trigger the epiphyseal plates to close, sealing the deal and bringing longitudinal growth to a permanent halt. Females generally experience this closure earlier due to estrogen's stronger effect on plate closure, which partly explains why females typically stop growing taller earlier than males.
That's a complex interplay. Grow fast, then stop.
Okay, so we've covered growth and length, but bones also get thicker, denser, right? Especially with exercise.
Excellent point. We've been talking about longitudinal growth, but bones also grow in width or thickness throughout life. This is called appositional growth.
Appositional, adding layers.
Precisely. This isn't happening at the growth plates. Instead, osteoblasts, the periosteum, the outer membrane, secrete new bone matrix onto the external surface of the bone. It's like adding new layers to the outside of the pipe, making it thicker and stronger.
And this is driven primarily by mechanical stress and muscle activity. The more physical stress a bone experiences, the more the osteoblasts are stimulated to lay down new compact bone on the outside. At the same time, Osteoclasts might be subtly removing a bit of bone from the inner surface lining the medullary cavity, preventing the bone from becoming excessively heavy while still increasing its diameter and strength.
So this explains why a weightlifter's bones become demonstrably thicker and denser than someone who's sedentary.
Absolutely. Bone literally reshapes itself in response to the loads placed upon it. Use it, and it strengthens. Lose the stress, and it can weaken.
Which brings us back perfectly to the idea that even after growth plates close, the architectural work never truly stops. That concept of bone remodeling.
Yes, remodeling. It's fundamental. It's the body's perpetually active internal renovation crew, constantly at work throughout your entire life.
Renovation crew. I like that.
It fits. Remodeling is the ongoing replacement of old, worn, or micro-damaged bone tissue with new, healthy bone tissue. And it's driven entirely by the coordinated, balanced activity of those two key cell types we discussed: the osteoclasts, demolition crew, and the osteoblasts, construction crew.
We hear the term remodeling a lot in biology, but what's the actual scale of this turnover? How much of our skeleton gets renovated?
It's quite significant. The rate varies depending on the bone, the specific region within the bone, your age, diet, hormones, and crucially, the mechanical stresses it experiences.
So faster in some areas than others.
Definitely. Highly stressed, compact bone, like the shaft of your femur, might remodel relatively slowly, perhaps turning over completely every 5 to 10 years. But spongy bone, which has a much larger surface area accessible to remodeling cells, especially in areas like your jaw, wrist, or vertebrae, can turn over much faster. Some estimates suggest 15 to 20% of spongy bone might be remodeled annually.
Wow, so on average,
Across the entire skeleton in a healthy young adult, it's estimated that about 5 to 10% of your total bone mass is recycled and replaced every year.
so significant chunks of our skeleton are actually completely new material every decade or so. That's mind-blowing.
It really is. It underscores that bone is not static. It's a highly dynamic, living tissue, constantly adapting and maintaining itself.
But what happens if that renovation crew gets out of balance? If the demolition outpaces the construction?
That's exactly where major clinical problems arise. If osteoclast activity resorption, the demolition consistently outpaces osteoblast activity deposition, the net result is a loss of bone mass and density. The bone becomes weaker, more porous.
And the most common example of that imbalance is?
Osteoporosis. It literally means porous bone. In osteoporosis, the resorption process significantly overtakes formation. The trabeculae in the spongy bone become particularly thin and fragile, sometimes breaking entirely, reducing the structural integrity.
Leading to fractures.
Exactly. Especially compression fractures in the vertebrae, causing loss of height and back pain, and fractures of the hip, specifically the neck of the femur, and wrist, often from relatively minor falls or stresses that wouldn't harm healthy bone. That continuous maintenance job, that balance between clasts and blasts, is quite literally the difference between healthy aging and debilitating structural failure.
That really makes the process feel incredibly high stakes.
Okay, we have a deep understanding now of the living material, its cells, its growth, its maintenance. Let's finally move to the main event, the macroarchitecture itself. Section 3, the axial skeleton deep dive, focusing on the specialized substructures of the head, the spine, and the torso's core.
All right. The exoskeleton, as we said, it comprises 80 named bones, and they form the central longitudinal axis of the body.
The core structure.
Exactly. It includes the skull, the unique floating highway bone, the complex vertebral column, spine, and the protective bony thorax, ribcage. This is the central pillar, the foundation upon which the appendicular skeleton, limbs, and girdles hangs. Let's begin at the top, the skull. The ultimate protective housing for the brain, but also much more. It seems like a masterpiece of interlocking plates.
It truly is. The skull is the most complex bony structure in the body. It consists of 22 bones in total, plus the ear ossicles usually counted separately. These 22 are functionally segregated into two critical groups.
Okay, what are the two groups?
First, the 8 bones of the cranium, or cranial bones. These form the protective vault that directly encloses and protects the brain.
The brain case.
Right. And second, the 14 facial bones. These form the anterior framework of the face, provide cavities for sensory organs, eyes, nose, mouth, secure the teeth, and anchor the facial muscles for expression.
Let's focus on the cranium first, the helmet. Which bones make that up?
The cranium forms the roof, sides, and base of the skull. It includes the single frontal bone, forehead, the single occipital bone, back of the head, the single ethmoid bone, deep between the eyes, and the single complex sphenoid bone, the keystone at the base.
And some paired bones.
Yes, plus the paired parietal bones, forming most of the superior and lateral walls, and the paired temporal bones, inferior to the parietals, housing the ear structures. Together, these 8 bones form a remarkably strong, unified, rigid box for the brain.
Okay. And the 14 facial bones. Maybe instead of listing all 14, we can think about their main jobs.
That's a good approach. Functionally, we can group them. Some primarily define the structures for our special sensory organs, like the paired zygomatic bones, your cheekbones, which form the prominent part of the cheeks, and the lateral walls and floors of the eye sockets, orbits.
Protecting the eyes.
Exactly. And the small lacrimal bones housing the tear ducts, and the nasal bones forming the bridge of the nose. Others are more involved in anchoring our teeth and forming the passages for air and food.
Like the jaws.
Right. The paired maxillary bones, or maxillia, are key. They form the upper jaw, anchor the upper teeth, and actually form the central part of the face. They also form part of the orbits and the nasal cavity walls.
And the lower jaw.
The mandible, the lower jaw bone. It's the largest, strongest bone of the face, anchors the lower teeth, and forms the only freely movable joint in the skull, the temporomandibular joint, or TMJ. We also have the palatine bones forming the back of the hard palate, the single vomer forming part of the nasal septum, and the inferior nasal conchae projecting into the nasal cavity.
That's a lot of intricate parts fitting together. How do the cranial bones specifically join up so tightly? It looks like they're fused.
They are, in adults. The joints connecting the major cranial bones are called cranial sutures. They look like these irregular, jagged, interlocking seams or joints.
Sutures, like stitches.
Kind of, yeah. Structurally, they're classified as fibrous joints. In infants and children, there's a bit more connective tissue, allowing for growth. But in adults, the bones fuse very tightly at these sutures, effectively locking the cranium into a single solid unit.
Are there specific names for the main ones?
Yes, our sources highlight the 4 most prominent ones. The coronal suture runs side to side like a crown, where the 2 parietal bones meet the frontal bone anteriorly.
Okay, front seam.
Then the sagittal suture, running front to back right along the midline of the skull, where the right and left parietal bones meet superiorly.
Top seam.
Right. Posteriorly, the lambdoid suture connects the parietal bones and temporal bones with the occipital bone. It looks a bit like the Greek letter lambda.
Back seam.
And laterally, the squamous suture is where each parietal bone meets the temple bone below it on each side.
Got it. And you mentioned these allow growth in babies.
Exactly. In infants, these sutures are wider and contain more fibrous tissue. Where multiple sutures meet, you have larger membrane-filled spaces called fontanelles, the soft spots.
Ah, the soft spots.
Right. These allow the fetal skull to deform slightly during passage through the birth canal. And importantly, they accommodate the rapid brain growth that occurs during infancy. They gradually ossify and close up, typically by about 18-24 months.
Okay, moving inside the skull now. Looking down at the base of the cranial cavity, it's not a smooth bowl, is it?
Not at all. The internal base of the skull, the cranial floor, is remarkably complex. It's shaped into 3 distinct levels or depressions, like terraces separated by bony ridges. These are the anterior, middle, and posterior cranial fossa.
Fossae, like basins.
Exactly. These basins are precisely shaped to cradle and support specific parts of the brain. The shallow anterior cranial fossa holds the frontal lobes. The middle cranial fossa is shaped like butterfly wings and holds the temporal lobes. And the deep posterior cranial fossa holds the cerebellum and brainstem.
So the brain fits snugly into these contours.
Very snugly, and shows it's well supported and protected.
Beyond the main cranial vault that holds the brain, the skull is apparently riddled with other cavities and spaces.
Oh, yes. Several smaller cavities are housed within the skull bones. We have the middle and inner ear cavities carved into the temporal bones. We have the orbits, the bony sockets that house the eyeballs and associated muscles and fat.
The eye sockets.
Right. We have the complex nasal cavity divided by the nasal septum, and then we have the paranasal sinuses.
Ah, the sinuses. Everyone's favorite during allergy season.
Tell me about it. These are air-filled cavities located within specific skull bones surrounding the nasal cavity. They are named for the bones they're in. The frontal sinuses in the forehead, ethmoidal sinuses between the eyes, synoidal sinuses deep behind the nose, and the large maxillary sinuses in the cheekbones.
What's their purpose? Just to get infected?
Well, their exact functions are debated, but generally they're thought to lighten the overall weight of the skull, act as resonance chambers for speech, and perhaps help warm and humidify inhaled air. But yes, because they're lined with mucous membrane continuous with the nasal cavity, they can easily become inflamed and block sinusitis.
Okay, cavities explained. Now, the most surprising statistic you mentioned earlier was the sheer number of holes or openings in the skull, something like 85.
That's right. Approximately 85 named openings are called foramina, singular foramen, canals or fissures. The skull looks solid, but it's strategically perforated.
Why? Why punch so many holes in the armor?
Because crucial structures need to pass into and out of the cranial cavity. Think of it as the ultimate utility port system for the central nervous system and its support structures.
Utility ports? Like for wiring and plumbing?
Exactly that. The largest and most obvious opening is the massive foramen magnum, great hole, located at the base of the occipital bone. This is where the brainstem exits the skull and connects with, becomes, the spinal cord.
The main data cable connection?
Precisely. But countless other, smaller foramina and canals provide vital passageways for the 12 pairs of cranial nerves, which transmit sensory and motor information to and from the brain, and for the major blood vessels, arteries bringing oxygenated blood in, veins taking deoxygenated blood out, that serve the brain and facial structures.
So if the skull is the protective armor, these foramina are the absolutely necessary access points for the nervous system's wiring harness and the critical blood supply lines.
Couldn't have said it better. Their functional integrity is non-negotiable for life. Any blockage or compression here can have devastating consequences.
Okay. Before we move down from the head region, we absolutely have to acknowledge what you called the most rebellious bone in the body.
Ah, yes. The hyoid bone.
The floating anchor. Where is it exactly, and what makes it so unique?
It's located in the anterior neck, just inferior to the mandible, lower jaw, and superior to the larynx, voice box. You can sometimes feel it if you gently palpate high up under your chin.
And its claim to fame.
Its unique feature is that it is the only bone in the entire human body that does not directly articulate or form a joint with any other bone.
No joints at all. How does it stay put?
It's suspended, anchored entirely by ligaments and muscles connecting it to the temporal bones, the mandible, the sternum, scapula, and the larynx. It literally floats in the neck musculature.
Wow. So why have a floating bone? What's its function?
Its function relies entirely on this unique suspension. It serves as a movable base for the tongue, many tongue muscles attached to it, and acts as a crucial attachment point for numerous small muscles in the neck and throat that are involved in swallowing and speech modulation.
So it needs to move freely for us to swallow and talk properly.
Exactly. It gets pulled up during swallowing, for instance. It's a fascinating little anatomical marvel of suspension mechanics. A floating pivot point.
That really is a cool anatomical outlier. Okay, let's transition now down the central axis to the structure that transmits all our upper body weight and houses that critical central data highway. Section 4, the vertebral column, the spine.
Right, the vertebral column, or spine. In the adult, it's typically formed from 26 separate, highly complex, irregular bones, though it starts as 33 in the fetus before some fuse.
26 bones stacked up. What are its main jobs?
Its functions are absolutely profound. First, it provides flexible support for the trunk and head. Second, it protects the extremely delicate spinal cord running within its central canal. Third, it transmits the entire weight of the trunk down to the pelvis and lower limbs. And fourth, it serves as the crucial attachment site for the ribs and the numerous muscles of the back and neck.
That's a lot of responsibility for one column. It must be a complex support system held together by more than just the bony blocks themselves.
Oh, absolutely. The stability of the column isn't just from the interlocking vertebrae. It's heavily reliant on extremely tough, fibrous ligaments, like the long anterior and posterior longitudinal ligaments that run the entire length of the spine, preventing hyperextension and hyperflexion.
Ligaments binding it together.
Yes, plus strong ligaments connecting adjacent vertebrae, like the ligamentum flavum. And then you have the flexible intervertebral discs acting as shock absorbers between the vertebral bodies and numerous synovial joints between the articular processes of adjacent vertebrae, allowing for movement. It's a composite structure of bone, cartilage, and ligament.
Let's look at the standard building block then. What does a typical vertebra look like? What are its key parts?
While there's significant regional variation, a typical vertebra, say from the thoracic or lumbar region, has a common structural plan. Anteriorly, there's a large disc-shaped body. This is the main weight-bearing part.
The solid block in front?
Right. And these bodies get progressively larger as you move down the spine, reflecting the increasing load they have to support. Posterior to the body is the vertebral arch.
The arch forms a hole.
Exactly. The body and the arch together enclose a large opening called the vertebral foramen. When all the vertebrae are stacked up, these foramina align to form the continuous vertebral canal, which houses the spinal cord.
Protecting the cord inside the tunnel.
Precisely. The vertebral arch itself is formed by two short, stout processes called pedicles projecting back from the body, and two flat plates called laminae that meet in the middle posteriorly.
Pedicles and laminae form the arch.
Okay.
And sticking off this arch.
Extending from the arch are several important processes. Typically, there are 7. Two transverse processes project laterally from the junction of the pedicle and lamina. These are sites for muscle attachment and rib articulation in the thoracic region.
Okay, sideways projections.
One prominent spinous process projects posteriorly and usually inferiorly from the midline where the two laminae meet. This is the part you can often feel as a ridge down the center of your back. Also important muscle attachment points.
The bumps on the spine.
Right. And then there are 4 articular processes, 2 superior and 2 inferior, which have smooth joint surfaces, facets. These articulate with the articular processes of the vertebrae immediately above and below, forming those synovial joints that allow for spinal movement while also restricting excessive motion.
Wow, okay. Body, arch, canal, and 7 processes. That's the template. But you said there's regional variation?
Huge variation. The structure is highly specialized based on the specific region and the forces it must handle. The 26 bones are grouped into 5 regions.
Let's run through them. Top down.
Top down. First, we have the 7 cervical vertebrae in the neck, designated C1 through C7. These are the smallest, lightest vertebrae, adapted for supporting the head and allowing a wide range of motion.
Cervical, C1 to C7. Neck.
Then 12 thoracic vertebrae, T1 through T12, in the chest region. These are larger than cervical, and they're unique because they articulate with the 12 pairs of ribs. Their spinous processes tend to point sharply downward.
Thoracic, T1 to T12. Ribs attach here.
Next, the 5 lumbar vertebrae, L1 through L5, in the lower back. These are the real heavyweights, massive bodies designed to bear the brunt of the upper body's weight. They allow for flexion and extension, but limited rotation.
Lumbar, L1 to L5. Lower back, weight-bearing.
Inferior to the lumbar vertebrae is the sacrum. This is a large triangular bone formed by the fusion of 5 separate sacral vertebrae, S1, S5, during adolescence. It forms the strong posterior wall of the pelvis and transmits body weight to the hip bones via the sacroiliac joints.
Sacrum, 5 fused into 1. Connects spine to hips.
And finally, dangling off the inferior tick of the sacrum is the tiny coccyx, or tailbone. This is also a fused bone, typically formed from 3 to 5, usually 4 small, rudimentary coccygeal vertebrae. It's mostly vestigial, but provides some attachment points for pelvic floor muscles.
Coccyx, 3 to 5, fused. Tailbone. Okay, 7, 12, 5, 1 fused, 1 fused. That's 26 total bones in the adult column.
That's the count.
Now, within the cervical region, C1 and C2 are apparently super specialized, right? We need to pause on them. You call them atlas and axis.
Yes, they are highly modified and unique, deserving special attention because they allow for head movements.
Go.
C1, the atlas, is named after the Greek Titan who held up the heavens, aptly named because it supports the globe of your head.
What makes it different?
The atlas C1 is unique because it has no body and no spinous process. It's essentially just a bony ring consisting of an anterior arch, a posterior arch, and 2 large lateral masses.
A ring holding the head.
Yes. The superior articular facets on its lateral masses are large and concave. They articulate directly with the rounded occipital condyles on the base of the skull. This joint allows you to nod your head yes, flexion, and extension.
Okay, atlas lets you nod yes. What about C2?
C2, the axis, is also highly specialized. Its main distinguishing feature is a prominent tooth-like superior projection called the dens, or the odontoid process.
Dens, like a tooth.
Exactly. This dens projects upward from the body of the axis, fitting snugly into the anterior part of the ring of the atlas above it. It's held securely in place by a strong transverse ligament.
So the ring of atlas sits over this peg from axis.
Precisely. The atlas, carrying the skull, then pivots or rotates around this dens of the axis. This atlanto-axial joint is what allows you to rotate your head from side to side, as if shaking your head no.
Atlas for yes, nodding at occipital condyles. Axis for no, atlas rotating around the dens. That's elegant.
It's a truly elegant mechanical solution, combining stability with significant rotational freedom right at the base of the skull. Relies heavily on ligaments to keep that dens safely positioned away from the spinal cord passing just behind it.
That intricate interlocking is crucial. Okay, zooming back out to the whole vertebral column. Looking at it from the side, it's definitely not a straight rod. It has distinct curves. Why the S shape?
That S shape, formed by 4 normal curvatures, is absolutely critical for function. It dramatically increases the resilience and shock-absorbing capacity of the spine.
How so? Like a spring?
Exactly like a spring, or like the spring suspension system in a car. A perfectly straight, rigid column would be very prone to buckling under compression. and would transmit jarring impacts directly up to the skull. The curves allow the spine to distribute weight and absorb shocks much more effectively.
How much more effectively?
Estimates suggest the curved spine might be 10 to 15 times stronger and more resilient to vertical compressive forces than a straight column of the same length and material.
Wow. Okay, what are the 4 normal curves?
Viewed from the side, we have the cervical and lumbar curvatures, which are concave posteriorly. They curve inward toward the front of the body.
Neck and lower back curve in.
Right. And we have the thoracic and sacral curvatures, which are convex posteriorly. They curve outward toward the back.
Chest area and pelvic area curve out. Got it. Cervical concave, thoracic convex, lumbar concave, sacral convex, the S-shape.
That's the normal adult pattern. Interestingly, we aren't born with all of them.
Oh. How do they develop?
In the fetus, the spine just has one continuous convex curve posteriorly, like the letter C. The thoracic and sacral curves are therefore called primary curves. The secondary curves, the cervical and lumbar, develop after birth as the infant gains muscle control.
When do they appear?
The cervical curve develops when the baby starts to lift its head and hold it erect, around 3 to 4 months. The lumbar curve develops later when the child learns to sit up, stand, and walk, around 1 year, as it adapts to supporting the body's weight in an upright posture. The structure literally evolves based on the new mechanical demands placed upon it.
That's fascinating. The curves are acquired through use. Now, sometimes these curves become exaggerated or abnormal, right?
Yes, unfortunately. Abnormal spinal curvatures can cause significant problems. Our sources mention 3 main types. Scoliosis, which is an abnormal lateral curvature, often accompanied by rotation of the vertebrae, making the spine look like an S or C shape from behind.
Sideways curve.
Right. Then kyphosis, which is an exaggerated thoracic curvature, leading to a hunchback appearance, often seen in older individuals due to osteoporosis, but can occur at any age.
Exaggerated outward curve in the upper back.
And lordosis, which is an exaggerated lumbar curvature, creating a swayback appearance, often associated with pregnancy or significant abdominal obesity, shifting the center of gravity.
Exaggerated inward curve in the lower back. Got it. Scoliosis, kyphosis, lordosis.
Right. These abnormal curves can cause pain, breathing difficulties, and put abnormal stress on the vertebrae and discs.
Speaking of discs, nestled between almost all the vertebral bodies are those essential cushion-like pads. The intervertebral discs, how important are they?
Incredibly important. They perform 2 main functions. They act as powerful shock absorbers during activities like walking, running, and jumping, and they allow for flexibility and movement between adjacent vertebrae. They actually account for about 25% of the total height of the vertebral column.
A quarter of the height is disc. Wow, what are they made of? They seem like tough jelly donuts.
That's not a bad analogy, actually. Structurally, they are composite structures, designed a bit like a radial tire. They have 2 main parts. The outer part is the annulus fibrosus.
Annulus, like a ring.
Exactly. It's a strong outer ring composed of concentric layers of fibrocartilage, with the collagen fibers in adjacent layers running in different directions. This cross-ply arrangement makes the annulus incredibly tough and able to withstand twisting forces and contain the inner core.
The tough outer wall, what's inside?
The inner core is the nucleus pulposus. This is a gelatinous, semi-fluid material. It's about 70–80% water in young adults, though it dehydrates with age. It's highly elastic and compressible. Interestingly, it's a remnant of the embryonic notochord.
The jelly filling.
Right. This gel-filled core is what gives the disc its high compressibility, its elasticity, and its ability to act as a shock absorber. When you jump, the nucleus pulposus compresses and transmits the force outward to the annulus fibrosus.
Okay, shock absorber and flexibility joint. But what happens when that radial tire blows out or the jelly donut leaks? This is the infamous herniated disc, right?
That's exactly it. A herniated or slipped disc, though it doesn't really slip, it ruptures, occurs when the tough outer wall of the annulus fibrosus weakens or tears, often due to excessive pressure, sudden trauma, or age-related degeneration.
The outer wall breaks down.
Right. And when that happens, the semi-fluid gelatinous material of the nucleus pulposus can bulge or be forced out. It herniates posteriorly or posterolaterally.
And why is that bad?
Because the vertebral canal and the intervertebral foramina, where spinal nerves exit, are very tightly packed spaces. When this disc material bulges out, it can directly impinge upon or compress the highly sensitive spinal cord, or, more commonly, the spinal nerve roots exiting nearby.
Pressing on a nerve.
Exactly. And that compression is what causes the characteristic symptoms. Intense, often radiating pain, like sciatica if it affects the sciatic nerve down the leg, numbness, tingling, and potentially muscle weakness in the area supplied by the compressed nerve. It's a very direct and painful illustration of mechanical failure within this precisely engineered structure.
Oof. That makes the structure-function connection very real and potentially painful. Okay, a crucial component. Let's finally wrap up our tour of the axial skeleton with Section 5, the thoracic cage, the protective housing for our upper vital organs.
Right, the thoracic cage, sometimes called the bony thorax. It forms a protective cone-shaped enclosure around the organs of the thoracic cavity. The heart, lungs, major blood vessels like the aorta and vena cava.
What are its components?
It's formed by the 12 thoracic vertebrae posteriorly, the 12 pairs of ribs curving around laterally and anteriorly,
Right.
and the sternum breastbone anteriorly in the midline.
The sternum, the flat bone in the middle of the chest.
Exactly. The sternum, or breastbone, is this flat, elongated bone often described as being shaped like a dagger or a necktie.
A dagger.
Yeah, it has 3 fused parts. The superior broadest part is the manubrium, the handle of the dagger. The long central part is the body, the blade. And the small inferior tip is the xiphoid process, the point, which remains cartilaginous until middle age and then ossifies.
Manubrium, body, xiphoid, and its main job.
It serves as the crucial anterior anchor point for the ribs and the clavicles, completing the cage at the front. And of course, it provides direct protection for the heart lying just behind it.
Okay, sternum anchors the front. Now, the ribs, 12 pairs.
12 pairs, yes. They form the curving walls of the thoracic cage. All 12 pairs articulate posteriorly with the 12 thoracic vertebrae. Their anterior attachments, however, vary, and that's how we classify them.
How are they classified? True, false?
Right. The first 7 pairs, ribs 1 to 7, are called true ribs, or vertebrosternal ribs. They are true because they attach directly to the sternum anteriorly via their own individual strip of hyaline cartilage called costal cartilage.
True ribs, direct connection to sternum via cartilage. Okay.
Then the next 3 pairs, ribs 8-10, are called false ribs, specifically vertebrachondral ribs. They are false because their costal cartilages do not attach directly to the sternum. Instead, each rib's cartilage attaches to the cartilage of the rib immediately above it, so they have an indirect connection.
False ribs. Indirect connection via cartilage of rib above. Got it. That's 10 pairs. What about the last 2?
The final 2 pairs, ribs 11 and 12, are also technically false ribs, but they get a special name, floating ribs, or vertebral ribs.
Floating? Why floating?
Because they have no anterior attachment whatsoever. Their costal cartilages are very short and just end within the muscles of the lateral abdominal wall. They only connect posteriorly to the thoracic vertebrae.
So they don't connect to the sternum at all, directly or indirectly?
Correct. They just float at the front.
Huh.
But this isn't a design flaw.
No. What's the point of floating ribs?
They still provide essential protection for the posterior abdominal organs located in that region, like the kidneys. And their lack of a fixed anterior connection allows for greater flexibility and expansion of the lower thoracic cage and upper abdomen, which is important for processes like deep breathing or accommodating abdominal distension.
Ah, protection plus flexibility. Makes sense. So the whole cage provides protection, but also has built-in flexibility, mainly through those costal cartilages, allowing it to expand and contract during breathing.
Precisely. It's a protective shield that can still move. A dynamic armor.
We've covered a lot of ground, or rather, a lot of bone. We've traveled the entire length of this central structure, the axial skeleton. We started way down at the microscopic level with the construction crew.
The osteoblasts and osteoclasts.
Right, and moved through the bone's continuous life cycle, its growth spurts driven by hormones, its constant remodeling.
The renovation crew, always at work.
Exactly. And then we explored the macro architecture, detailing the intricate helmet of the skull with all its utility ports.
The amazing pivot mechanics of C1 and C2 for head movement.
The brilliant spring suspension system of the S-shaped spine, the crucial shock absorbers of the intervertebral discs.
And finally, the protective yet dynamic thoracic cage.
So wrapping this all up, what's the single most important takeaway for you, for the listener, about this core framework?
I think the primary takeaway has to be that your skeleton, especially this central axial core, is fundamentally dynamic. It is absolutely not a static, inert scaffold like you might see in a model.
It's alive.
It's alive. It's a highly specialized, complex, self-regulating living system. It maintains critical mineral balance for your entire body. It produces virtually all your blood cells, and it is perpetually remodeling itself minute by minute, day by day, to adapt to the forces of gravity, movement, and biochemical signals. It's far, far more intricate and active than just a simple framework.
And thinking back to the hormonal regulation, it was striking how tiny glands like the pituitary and thyroid located far from the bones themselves.
Mm,
And these small surges of sex hormones during puberty, how they can dictate the precise rate and proportion of bone growth. They literally determine the final rigid architectural plan of your skeleton, even signaling when the growth plates must fuse and lock in that final structure.
it's true. The entire blueprint is set in motion, modulated, and ultimately finalized by these invisible, potent chemical signals we call hormones.
Which leads to a really interesting final thought, building on that.
Okay.
Well, if such small chemical signals hormones operating at a cellular level can exert such profound control over the shape, the density, and even the final seemingly fixed length of the most rigid parts of your body, your bones,
Yeah.
then the provocative question for you, the listener, to maybe mull over is this. What other invisible, perhaps hormonal or biochemical forces might be subtly influencing the structure, the function, maybe even the perceived limitations of other parts of your body that you currently think are completely fixed and unchanging?
Like what?
Maybe your tendons, your ligaments, the fascia that runs throughout your body, perhaps even aspects of your brain structure or neural pathways. If bone is so dynamic and responsive to these signals long after we think growth has stopped,
Yeah.
what else might be?
That's a fascinating point. It really highlights the incredible complexity and the interconnectedness of every system in the body, doesn't it? Nothing exists in isolation. It really does. Food for thought indeed. Thank you for joining us for this deep dive into the living architecture of the axial skeleton.
It was a pleasure. We look forward to seeing you for the next one.